James Cameron's 1991 blockbuster, Terminator 2 Judgment Day, is a titular sequel to 1984's classic Arnold Schwarzenegger flick, The Terminator. Set in the latter half of the 20th century, the Terminator franchise follows John Connor and his mother Sarah through their encounters with time-traveling cybernetic assassins. The first of these machines, known as the T-800, portrayed by Arnold Schwarzenegger, was featured as the first film's antagonist, but appears in the sequel as a guardian for John Connor. A new android model, the T-1000, replaces Arnold in the villainous role for the sequel. This new Terminator, brought to life by actor Robert Patrick, challenges Schwarzenegger's obsolete form with a slew of interesting skills enabled by material properties.
In this scene, we see one of the T-1000's primary abilities. When faced with a solid obstacle, the machine uses its liquid state to phase through the security bars. Following this feat, it also endures a number of blasts from a shotgun, with noticeable deformation appearing from each shot. Before escaping, Arnold Schwarzenegger's Terminator delivers an effective shot, which requires the T-1000 to pause and heal. Literature pertaining to the franchise cites a mimetic polyalloy as the material responsible for the powers of the T-1000. This material is further described as an artificial liquid metal compound which has the ability to mimic the shape of any object it contacts. In the penultimate scene of the film, a grenade blast appears to do irreparable damage to the machine, with the descent into a vat of molten steel ultimately ending the technological tear. The invention of mimetic polyalloy seems dubious at best, doing little to answer the question of how such a machine and material would work. By inference of the construction of other Terminator models and some hypotheses of our own, we believe this character's feats may fall closer to physical reality than one would think.
Surrounded by a liquid nitrogen environment, the T-1000 periodically slows down and eventually actually freezes. Most interestingly here, the T-1000 begins to shatter itself just under its own weight and propulsion. As we'll discuss later, this seems to fall in line with an idea for a total construction of some kind of underlying nanotech skeleton with an outer liquid metal encompassing it. Following the liquid nitrogen scene, while in proximity to a steel mill, the T-1000 begins to melt or thaw and melt and eventually reforms. Here we note that it has a very shiny metal appearance, its reformed state, after this liquid nitrogen has evacuated. Interestingly, another T-1000 appears in the 2015 sequel Terminator Genisys. Here, exposure to some strong acid seems to immediately strip this Terminator of its liquid metal, leaving only a skeleton of sorts underneath, which we believe to be some sort of a nanotech construction. The performance of this skeletal body implies it may be physically more resilient than the outlying liquid metal, as it's able to resist the acid. Ultimately, as a matter of thermodynamics, there appear two possible descriptions for the nature of the liquid metal used by the T-1000. Drawing from a science fiction power source or a more real solution like nuclear diamond batteries, the T-1000 may exert energy from this power source in its skeleton to change the state of its mystery alloy, suggesting a metal with a low melting point that solidifies near normal temperatures and pressure. Alternatively, the use of a metal which liquefies below room temperature and would hence require cooling by the accessory systems of the skeleton could provide a superior explanation. Referring to the liquid nitrogen scene, it seems odd that a machine outfitted with enough power to melt its constituent metal could probably overcome the refrigerated environment a little better than he appears to. The second design, however, better agrees with the portrayed behavior and works to explain the solidification of the machine once inside the steel mill, where we'd otherwise maybe expect it to just melt into an utter pile of goop. Um, and for these reasons, the ability of the T1000 to cool itself is far more significant than the alternative setup, especially in terms of the time frame that it takes for it to reform after sustaining any damage. From this conclusion, a real-world alloy has presented itself as a possible alternative candidate for the T1000. Well, a number of alloys exist with relatively low melting temperatures, like pure gallium, Fields metal, and a number of commercial solders. The gallium, indium, and tin alloy, known commercially as Gallistan, provides a unique solution in our search.
Gallistan features a melting point of negative 19 degrees Celsius, but retains its composition until a boiling point of 1300 degrees Celsius, only marginally less than the melting point of most steels. While in liquid form, Gallistan takes on a glossy silver appearance, consistent with the liquid form of the Terminator. This property allows Gallistan to be painted on surfaces, such as glass, in order to make mirrors. It also enables Gallistan to be a non-toxic replacement for mercury in thermometers. Similar to its primary constituent, gallium, Gallistan exhibits a face-centered orthorhombic crystal structure. Not unlike a face-centered cubic crystal, the FCO structure is axially stretched. A face-centered orthorhombic unit cell has a coordination number of 4. There is no standard atomic packing factor for FCO structures, as the side lengths of the unit cell may vary. However, the atomic packing factor for an FCO structure can be calculated by the formula 16 pi r cubed divided by 3 times A times B times C, where A, B, and C are the side lengths of the unit cell. In truth, micrographs of this material are rather hard to come by. However, likening the FCO crystal structure to face-centered cubic, a potential micrograph of Gallistan during its brittle fracture of the liquid nitrogen seen in the Terminator 2 could resemble a brittle fracture of steel, a face-centered cubic metal. The micrograph shown is the brittle fracture that occurs after steel is exposed to liquid nitrogen in our Sharpay impact testing lab. As Gallistan is a less utilized material than most other common metals, phase diagram information for this metal is scarce. However, a phase diagram for this material would feature a ternary phase diagram as opposed to the binary phase diagrams we typically deal with. An example for Gallistan would look similar to this phase diagram shown if A represents indium, B represents gallium, and C represents tin.
Hasta la vista, baby.